The question is, could you do an example illustrating the calculation of stress for a real problem? In this example, I will consider a 1D rod, one-dimensional rod that is segmented along the length. So this is the problem I have chosen here. We have a cylindrical bar with three different segments, AB, BC, and CD, each with different diameters. The bar is subjected to point loads at the ends of each segment. The question is to determine the maximum average normal stress in the bar. The first step in calculating the stresses is to determine the internal forces, right? Since we have point loads acting at these points A, B, C, and D, the internal forces are likely to vary from segment to segment, right? So what do? We take one segment at a time, section the bar at a point somewhere within the segment, separate the bar into two parts, the left part and the right part, and consider either the left part or the right part to evaluate the internal force or forces, right? And here are my sectionings. In the first figure, I sectioned it within segment AB. In the second figure, I sectioned it within segment BC. And in the third figure, I sectioned it within segment CD. Now we can either use the left side or the right side in each case to evaluate the internal force. So how do we decide on that? Well, one side or the other usually works out to be simpler to analyze. For example, in the first case, the left side is definitely simpler because it's only one external force in addition to this internal force NAB, right? In the second case, however, the left and the right side will involve the same number of terms in the equilibrium equation, so it doesn't matter which side you use. And in the third case, the right side is definitely easier to work with. Alright, so now what do? We choose one side and then write down the equilibrium equations to solve for the internal forces. Now, just by looking at the left side over here, you see the only external force we have is an axial force, right? And therefore, the shear force and the bending moment at that section are going to be 0. And therefore, only internal force you're going to have here is the axial force NAB. So we don't know whether they are compression or tension at this point. I usually go ahead and mark them as tension, and if the number that I get in the end is a positive number, then I know the direction that I have assumed initially is correct. If I end up getting a negative number, then I know it's not tension, it's compression, right? Alright, so with this background, here is my analysis for the first case. I considered the left side, summed up the forces in the x direction, which is the horizontal direction here, and I get NAB minus 10, NAB minus 10 equals 0, so that tells me NAB is 10 kilonewton. And I repeat this for the other two cases and consider the left side again for the second case. I get a value of minus 15 kilonewton for NBC, and therefore this is a compression. And then in the third case, I considered the right side, and I get a value of minus 3 kilonewton for NCD, and therefore that is a compression as well. So one important point we note here is that sectioning at any point within a segment will lead to the same value for the internal force. In other words, I could section it over here in the first case, or here, or here, or here, right? It doesn't matter which point you pick for sectioning, you can end up with the same results, right? Because the only external forces acting on the bar are at these intersections, right? So what that means is the internal force is a constant within each segment, right? So here's a summary of the internal forces we just calculated. NAB is 10 kilonewton tension, NBC is 15 kilonewton compression, and CD is 3 kilonewton compression. Our step number 2 is to go ahead and calculate the normal stresses in each of the segments A, B, B, C, and CD. We recall the definition of stress. Stress equals force per unit area. We also note that the internal forces are normal to the sectional planes. Like for example, if I take case number 1, this is our sectional plane and NAB is acting perpendicular to that, right? And therefore the corresponding stress arising from this normal force must be a normal stress. So here are my calculation. Sigma AB equals NAB over little a AB, the cross-sectional area of segment AB. So it will be 10 kilonewton divided by pi r squared, right? Or the radius of the first segment is 5 millimeters. So I converted that to meters. So that will be 0.005 meters. You square that, right? So pi times r squared is the cross-sectional area of a circular shaft. And that gives me this value for the stress. 127.4 times 10 to the 3 kilopascal. Remember, the units that we get out of this is kilonewton per meter squared, right? Which is kilopascal. And since I have this factor 10 to the 3, here we could express this as a megapascal stress, right? So that will be 127.4 megapascal. And you repeat that for the other two segments, and I get 7.64 megapascal here and 4.25 megapascal for the segment CD. So out of the three values, this is the largest of the three, and therefore it's clear that the maximum stress occurs within the first segment, and the value is 127.4 megapascal. And because the force is a tensile force, this is a tensile stress.